Hey, hello everybody to today's ISGC seminar talk. Today's speaker is João Luís Rosa. He did his PhD in 2019 in Centra, and he will talk about his work at Tartu University at Gdansk University. And this topic is observational properties of horizonless compact objects. Thank you, João, for agreeing to give this talk. The stage is yours.
Thank you. So yes, I'm going to speak about a series of different works that have been done in the past 5 years. These are works that I've been doing with different people in different institutes. I would like to mention a few. So we have Caio Macedo. He's one of the specialists in ray tracing and geodesic motion, and he was involved in our works with gravastars and with boson stars. Diego Rubera Garcia, he's a specialist in accretion disks, and in the section I will speak about accretion disks. He is the main specialist, and he's the person who contributed the most for this task. Annalise Tam is my student from Estonia, and she's contributed the most with the analysis of fluid stars. Daniela Perez and Joaquin Pelé, they are the specialists in spectroscopy. So there is a section where I will talk about line broadening of spectral lines, and these two people are the people I collaborated with. Then we have Vitor Cardoso, Nicolás Aymar, Paulo Garcia, and Frederic Vincent. The four of these are members of the Gravity Collaboration. Vitor Cardoso, Paulo Garcia, and Frederic Vincent, they are the ones that I started working with for the analysis of boson stars. Nicolás Aymar joined later for the analysis of polarization. Finally, we have Francisco Lobo and Daniela Cordeiro. Francisco Lobo is my former supervisor, and Daniela Cordeiro is my student, and they both contributed with the analysis of gravastars. So to introduce the topic, let's say that we have now observations that seem to indicate that objects that at least behave like black holes exist in the universe. And a few of the observations that we have pointing in that direction are the orbits of the S2 star. We have measured the orbit, or they have measured the orbit of the S2 star very precisely, and they have concluded that the trajectory of the S2 star is very close to what we expect from a movement in general relativity around the Schwarzschild black hole. Later in 2019, we had the first observation of a black hole shadow by the Event Horizon Telescope. And again, this observation is very close to what you expect from a black hole spacetime. And finally, in 2020, we had the observations of flares, infrared flares close to our own galactic center. And again, these observations are very close to what you expect if the object that we have in our galactic center is a black hole. Now, the problem with black holes is that, as we know, black holes have features that are not very well explained from a fundamental point of view. For example, we have singularities, and when we see a singularity, a divergence in curvature, immediately we start thinking that perhaps something is not right there. And also we have an event horizon, and an event horizon is something that is associated with problems in quantum mechanics, loss of unitarity, and information loss paradoxes and all that. So even though the black hole spacetime explains all of these observations very well, the problems that we have, the fundamental problems that we have on the black hole spacetime are drawbacks. So the idea would be to develop an alternative model to the black hole scenario, a model that could also reproduce the same observations, but without having the drawbacks of the black hole spacetime. So without having singularities and without having event horizons. So what we did was to take all or a large number of types of compact objects in the literature, and we tried to analyze what the observational properties of these objects would look like under different astrophysical contexts. And we want to see what these objects need to fulfill, what requirements these objects need to fulfill in order for these objects to be what we call black hole mimickers. So they reproduce the same observations that we have in the black hole spacetime. So the first thing I want to talk about, so the first set of observables, let's say, that I want to talk about is the astrometric observables. And to do so, let's do a little experiment here. Let's make a simulation of what a star orbiting a central black hole and a star orbiting an alternative compact object. What does that orbit look like from a faraway observer? So if you have a black hole, this is what your orbit looks like. So this little star here is orbiting around the central black hole. So there is a central black hole somewhere in here in the center of this image. We are observing the equatorial plane with an angle of 80 degrees. So we are close to the equatorial plane as we look into the black hole. And this little star is orbiting on the equatorial plane with a constant orbital radius. So what do we see? Well, if the star is in front of the black hole, we basically see the star and that's pretty much it. But when the star moves behind the black hole, it gets distorted and the second image appears on the bottom. There it was. And when the star comes back in front, the secondary image, as we call it, so this that we see here, this image is called the secondary image. The secondary image disappears when the star comes in front of the black hole again. So if you have a black hole, so if you have something that has an event horizon in the center, this is all that you see. A primary image corresponding to the star and a secondary image that corresponds to this additional image that appears on the bottom when the star is moving behind the black hole. Now, if you have an alternative object that doesn't have an event horizon, something changes. Besides the primary image that we see here, and the secondary image that we see appearing when the star moves behind, there it is, the secondary image, we have additional contributions. And you will see them here. What? There it was. Did you see it? Let's wait one more orbit, one more period so we can see it again. So notice, when the star moves to the right, additional images appear here in the center. There it was. Did you see them now? So there's two images rolling around in the center, and you don't see these images if you have a black hole spacetime instead. And the reason why you don't see these images is because for you to see these images, you need the event horizon to be absent, because if the spacetime has an event horizon, the photons moving to the center of this compact object are captured by the event horizon and they never reach the observer. But if you don't have an event horizon, it's perfectly possible for you to have photons coming through the center of the object and reaching the observer. And that gives rise to additional images, additional imprints in the screen of the observer that you don't see in the black hole spacetime. Now, the question is, how can we use these additional images that are present when you don't have an event horizon to impose constraints on the models and to test all of these additional models? So the first observable that I would like to discuss is the integrated flux. So what is the integrated flux? In the image that we were seeing before, in the simulation that we were seeing before, the tracks, the images move on the screen of the observer, and each instant of time corresponds to a point where the star is at a certain position on the screen. So if you integrate the entire photons or the entire orbit of the star around the center, and you sum all of the photons that you receive through an entire orbit, you obtain what is called the integrated flux. So what does the integrated flux looks like for compact objects with different levels of compacticity? So we know that the black hole is the most compact object that we can have. When we have a mass, a radius that is equal to of the mass, you get the event horizon, and you obtain the highest possible compacticity in a compact object. But if your compact object has a radius that is larger than 2 times the mass, you have a compacticity that is slightly lower than the black hole, and different levels of compacticity will affect what the observation looks like. So let's say that you have an object, in this case, this is a boson star, or all of the analysis that I'm going to show you will be based on boson stars, and I will tell you why by the end of this presentation. I will make sure to mention why we use boson stars and not any other compact object. Or I can just say really quick now that independently of the type of object you have, what matters the most is compacticity. So if you have, for example, compact objects made of different materials, for example, if you have a star made of relativistic fluid or a boson star made of a fundamental field, they will look approximately the same, even though they are made of different fundamental fields. They will look approximately the same as long as they have a similar level of compacticity. So compacticity is what matters the most in the observation of these spacetimes. and not the type of fundamental field or the type of fluid that constitutes the fundamental object. So in here, I will take the boson star because it's the model that we have studied the most and we have more results to show. But all of the explanation I'm going to do throughout this presentation is exactly the same for any other compact object, being a fluid star, a gravastar, or another type of boson star. All of the explanation applies to those models as well. The only thing that matters, or the thing that matters the most, is how compact your object is. So let's start with an object that is not very compact. If the object is not very compact, this means that the level of light deflection you have when photons are traveling around the object is lower than if you have a higher compacticity. So in here, on the left side, you have the integrated flux when you are observing the star moving from an angle of 20 degrees. So we are on top of your observation. The second one is at 50 degrees, and the third one is at 80 degrees. So what do we observe? Because the level of light deflection in this model, because it's a very low compacticity model, is not strong enough, you can only see the secondary image, so this image that appears when the star moves behind the central object, you can only see the secondary image when your observation is very close to the equatorial plane. But if you start increasing the compacticity of your central object, something interesting happens. At some point, the object is so compact that you can see the secondary images appearing even at low inclination. And when this happens, we say that our object is close to ultra compact, but it's still not ultra compact. What does ultra compact mean? Ultra compact means that the object is compact enough for you to develop light rings, for you to develop critical curves. And when this happens, then independently of the inclination on which you are observing the object, you always see not only the secondary images, and you can have several of those because there's no event horizon, you can see also several types of secondary image, and also the light ring contribution. So notice, unfortunately, the resolution of this image is not the best, but if you look closely in here between this line and this line, there is a very, very thin line of little points, and that corresponds to the light ring. That's something that you don't have in this model, but you have on the last one. So very low compacticity. You need high inclination to see the secondaries. Close to ultra compacticity, you can see the secondaries at any inclination, and ultra compacticity, not only you see the secondaries, you also see the light ring contribution. So this is what you see if you integrate your image for the whole orbit. But what is exactly detected on your telescopes? There's two things that are detected on your telescopes, and especially on the gravity instrument, so the the instrument that's being used for the observations of our galactic center. And these two observables are the magnitude and the centroid. What are they? The magnitude basically measures how intense is your light, and the centroid measures the position or the average position of light in your screen. So what happens if you have a single image? If you only have a single image, if you only have the primary image, like it happens for this model here at low inclination, if you only have a single image, what happens is that your magnitude increases or decreases based only on Doppler effect. So if you are at a certain position where the star is moving towards the observer, you have Doppler beaming increasing the intensity of your observation. If you are at a position where the star is moving away from you, you have the inverse Doppler beaming that decreases the intensity of your observation. So if you only have one image, this is what you see. There is a peak of intensity when you have Doppler beaming, and then a decrease when you have the opposite of Doppler beaming, or Doppler beaming in the opposite direction. Now, if you increase your inclination and you start seeing additional images, like it happens here, what happens to the magnitude? Well, you are following the primary image and you are following this beaming effect of the primary image, and then suddenly a new image appears on your screen. Well, if you have a new image appearing on your screen, this additional image corresponds to additional photons going to the observer, which causes an increase in your observed intensity. And that's why you see, for example, this peak here and this peak here. So this is the appearance and the disappearance of the additional images that you have. If you have, besides the primary and the secondary image, if you have the light ring contribution, so this very thin line around the observation, so this one that I mentioned here, that's very thin and very noisy, not only you have these peaks of images appearing and disappearing, but you also have some noise, and you can see it here. So notice how the red curve and the blue curve are very smooth, but the green curve starts having a lot of noise in here. And this noise that you see is exactly the photons coming from the light ring, because the light ring is very unstable. For the centroid, and this is something that you can see on the telescopes, so you can measure with your telescopes the intensity of light. The centroid, as I mentioned, is the position or the average position of the intensity in your observation. Again, if you only have a single image, or if the number of images that you have in your screen is constant, then the centroid follows very smoothly the position of your images, or the average position of your images, which is what you see here. But if at some point you have again the appearance or disappearance of images in your screen, then what happens to the centroid is that the centroid starts shifting. When you have an image on the right, only an image on the right, the centroid follows that image. But if at some point another image appears on the left, that pushes the average to the center. And that's exactly what we see here. So in this region, the centroid is following the primary image, and then at some point, boom, the centroid shifts closer to the center, meaning that there is the appearance of an image on the other side. And then when the centroid comes to this point and then boom, jumps again to the red line, this means that your image disappeared. So you can tell, based on the analysis of the centroid, if you have images appearing or disappearing on your screen. And finally, for the light rings, the same thing that I mentioned about in the magnitude also applies. If you have a light ring, the light ring is very noisy, and these lines cease to be smooth and start having the noise that you see in here. So, all of this to say that if you observe the center of our galaxy and you observe the magnitude as a function of time and the centroid as a function of time, you can use the data of this observation to conclude how many images you have on your screen, if these images appear or disappear, if you have or not light rings, and how these compare with the black hole spacetime. If you have differences, this could be an indication that the object that you have in the center of a galaxy is not a black hole, but could be something else without an horizon. Now, for the second part, or actually the third, counting the introduction as the first part, for the second part, I want to extend the analysis that we did on the second part, but including light polarization. Because in the same way that we made this analysis based on the intensity of light, a similar analysis can be made for the polarization components of light. So let's define the electric field vector of your wave in this way. So E is basically the intensity, or E squared is the intensity of light. We define two basis vectors, E alpha and E beta, which are perpendicular. And now we have this angle right here, chi0, which is called the EVPA, also known as the electric vector position angle. So let's define our electric field in this way, and we define the Stokes parameters, Q and U, to define the light polarization. So the angle chi0 is here, the I is the intensity, that is E squared, and then we define Q and U, so the Q and the U polarization based on these definitions. What do we observe? Well, what we observe is this. So in here on the first line, we have, on the first row, we have the intensity. So this is basically the same that we had in here for similar models, but it's basically the same thing. We have the intensity for the black hole on the left, for a very low compacticity horizonless object here, an object close to ultracompacticity, and an ultra-compact object. This is what we have for the intensity, and now we have also a row for the Q Stokes parameters, which is defined like this, and the U Stokes parameter defined like this. Again, what do we observe now? The number of images and the appearance or disappearance of images we have already analyzed for the integrated fluxes. The same conclusions apply here. So what else can we take from polarization of lights? Well, we can take something very interesting, or two things that are very interesting. First thing is that notice how in the black hole spacetime, you only have the primary and the secondary image, as I mentioned before, and the value of the Q parameter is negative for every position of the orbit. And then if you have additional images like you see here, or like you see here, or even like you see here, I'm sorry, the contrast in these images is not the best, but trust me, there are images here in the center. These images contribute with additional negative values for the Q parameter. So if you measure the Q parameter as a function of time, this Q parameter will be different, or the shape of this Q parameter will be different depending on the compact object that you have in the center. Same thing for the U parameter. So if you look at the U parameter, notice how for the black hole spacetime you have a negative arch right here and then positive arches here and here. Well, if you don't have an event horizon, so if you have an horizonless compact object, you have additional positive contributions here and here, an additional negative contribution there, and if you have a light ring and all of these additional light ring contributions, you can see that the positivity and negativity of the U parameter becomes very complex, as you can see here. So this image, for example, changes 4 times signal, and the same thing happens for this image on the bottom. So again, the structure of your U parameter changes as a function of the position in orbit, depending on point number 1, if you have or not an event horizon, and point number 2, how compact is your horizonless compact object. And if you measure these things, you can conclude, or you can infer, if the thing that you are observing in the center of a galaxy is a black hole or not. Now, this is not exactly what is observed in your telescope. This is just a pictorial example, in the same way that we had the integrated fluxes before. What is measured by your telescope, or by the telescopes in the gravity instrument, with the gravity instrument, what is measured are two things. First, the EVPA, so the electric vector position angle, and second, the QU loop. So you measure a point in the plane QU. And each point on this plane QU corresponds to a point in the orbit, to an instant in the orbit. And in here on the left side, we have the value of the electric vector position angle as the function of time, where this whole interval, this whole horizontal interval corresponds to a full orbit around the center. So what can we conclude when we take low inclination observations and when we take high inclination observations? First thing is that if you have a low inclination observation in what comes to the electric vector position angle, it really doesn't make a lot of a difference. There is a slight difference on the values of the EVPA and on the instance of time at which the EVPA makes a jump. So you see, like in here, it jumps down, and in here, it jumps down again. So the instant at which this happens changes slightly, but this is not too conclusive, let's say, because the values are very similar and the data is not very precise. But if we look instead at the position on the QU plane, then we start seeing something more interesting and with more potential to distinguish between different models. And what we see, for example, is that if your model is very low compacticity, like it happens for the SPS1, which is the model I showed you before, one of the low compacticity models for which you only have a primary image in your observation, we see something different than what happens for the other models. So if you look into this plot, this is the most important plot in this slide, you see that when the object moves around the center and makes all of these points in the QU plane, if you have a black hole, for example, which is the black line, this line makes two loops around the center. And these two loops are of different sizes. So you have one loop here of this size and another loop of a bigger size. Same thing for the image that is close to ultra-compact and the one that is ultra-compact. So we have, for example, for the blue line, which is close to ultra-compact, we have one loop, small one right here, and a bigger one right here. And this is consistent. But if you have a model or a compact object that is not compact enough to produce a secondary image, then you see that the two loops have the same size, which is exactly what we have here. And if the two loops have the same size, this is very important because it goes against the observations. We have ALMA observations and gravity observations. Both of them indicate that the QU loops have, or the loops in the QU plane, they have different sizes. So if you make a simulation and your model produces a QU plane with loops of the same size, your model is already contradicting observations. So we can very clearly say that this model SBS1 or any other model that is not compact enough to produce a secondary image, these models are excluded by observation at low inclination. Now, for high inclination, something also very interesting happens, which is the fact that, as you can see here on the bottom right plot, as you can see here, the differences between the models become very sharp. So you can see in here, the models are close to each other except for the SBS1 because the loops don't have the same size. But in here, on the bottom right, you can see that these three models, plus the black hole, the behavior on the QU plane is very different among all of the models. Unfortunately, we don't have any observations at high inclination to make a comparison with the data, but if eventually we find some target for our observations that is at high inclination, we could potentially use the observation of the values of Q and U, so the position on the QU plane, to make a more thorough distinction between different models. Unfortunately, at the moment, we don't have any high inclination observations to make this comparison with. Now, for the fourth part of this presentation, I want to talk about the shadows and accretion disks. And as I mentioned, the person that is the biggest specialist in this part is Diego Rubiera Garcia from the University of Madrid. He has been my main collaborator in this part of the work. So what we want to do here is to test the following hypothesis. We know that if you have a black hole and if you have an event horizon, you have a shadow. There is a region on the screen of your observer for which, if you trace your photons back, you cannot see any luminosity coming from this region because these photons would have to be emitted by the event horizon, and you know that's not possible. So you have to see a dark region, a dark spot on your observer screen if your central object is a black hole. Now the question is, what if this object doesn't have an event horizon? Do you still see a shadow? Do you still see a dark spot on your image if you don't have an event horizon? And the answer is, rather surprisingly, yes, you can still see a shadow even in the absence of an event horizon. Let's see how this works. So first thing that we need to do is to make a model for your accretion disk, for the intensity profile of your accretion disk. There are different models that explain the emission profile of an accretion disk. Recently, these three scientists have developed this model for the intensity as a function of the radius with three parameters, gamma, mu, and sigma. These three parameters control basically the rate of increase of your profile. So the larger the gamma, the faster the intensity profile increases as a function of the radius. Mu is basically your center point in your distribution, like a mean. Basically, that's why we call it mu, but it's not exactly the same as in a Gaussian distribution, but it's basically the central point. And sigma gives you that's why we call it sigma, like the standard deviation, gives you the width of your distribution. Now, there's two different things that we need to take into consideration here. First thing is that if you have an accretion disk, you can ask the question, where is your accretion disk? Is there a specific region of spacetime where the accretion disk stands? And the answer is yes. If your object has what is called an innermost stable circular orbit, so a radius at which the orbits become unstable, which is what happens, for example, in the black hole spacetime at r equals 6m, if you try to make an object orbit at a radius smaller than r equals 6m, this orbit is unstable, so the orbits are only stable if you have a radius larger than this Sgr A radius. So the first thing we can say is that, okay, if you have an accretion disk, a stable accretion disk, you need the accretion disk to be only in the region outside of the innermost stable circular orbit of the ISGO. So the first model that we consider for the accretion disk is a model, you can see the values of the parameters here, but it's basically a model that has a peak of intensity close to the innermost stable circular orbit. The intensity increases as you come from the infinity closer and closer to the innermost stable circular orbit, and this is because you have an increased velocity of the particles, increased friction, increase the intensity of the radiation being emitted by the particles there. But as you cross r equals 6m, you enter the region of unstable orbits, and so you expect the luminosity of your accretion disk to decrease very sharply. And that gives you the ISGO model of the accretion disk. Now, there is one more thing that we need to take into consideration when we are dealing with accretion disk models, and it is the fact that unlike black holes, which have event horizons, these models that we are interested in studying, they don't have event horizons. So if there is an accumulation, an accretion of matter, accumulation of matter inside your compact object, if this compact object is a black hole, you don't see this matter being accumulated. But if your compact object does not have an event horizon, you cannot exclude the possibility that all of this matter being accumulated in the center of your object will also have a certain temperature, and as such will also emit radiation. And you should be able to see this radiation because you don't have an event horizon. So to account for this effect, we have developed a second model, we call it the central model, and this model simulates an accumulation of matter at a very small radius that is emitting with a certain temperature. In fact, the superposition of these two effects, so accretion disk up to the ISGO or down to the ISGO, plus the central intensity, the central emission, the combination of the two or the addition of the two effects should be the realistic result. But since these two effects are additive, you can study them separately and see what effects you have on each of them. So let's see what happens if we calculate not the intensity in the reference frame of the accretion disk. So this intensity here, this intensity as a function of radius, this is what is emitted in the reference frame of the accretion disk, so in the reference frame of the central object. What does the observer see at a very large distance? And this is what the observer sees. So if you have a very dilute compact object, then you will see a very bright central intensity coming from the central model, which is what you see here. But if you start increasing the compacticity of your model, there is a very interesting effect, which is as you increase the compacticity of your model, you are decreasing the value of GTT of the metric component at the center where the radiation is being emitted, and that means that you have a stronger gravitational redshift effect. And because of this stronger gravitational redshift effect, even though you assume that radiation is coming from the center with the maximum intensity, you will still observe in the reference frame of the observer a decrease in the intensity coming from the center. And if you increase even further the compacticity, as it happens here for model SPS3, which is the ultra compact one, you can see a very, very low, almost zero value of intensity coming from the center. And notice that we are assuming that there is a peak of intensity at the center, but you just don't see it because of the effects of gravitational redshift. You still see a shadow even though there is no event horizon, and even though there is emission coming from the center. As for the ISGO model, so the model at which you assume your accretion disk is truncated at the value for the innermost stable circular orbits, these doesn't add any more information that we didn't have before already with the integrated fluxes. So for example, for the SPS1, you see that you only have a primary image at low inclination. For the SBS2, which is the close to ultra compact, you already see the primary, the secondary, and one additional image in the center. And for the ultra compact, you see all of the images plus the light ring, which is here. Cannot see it very well again because of the contrast of this image. But trust me, there is a light ring in here. So this ISGO model doesn't give you any more information that you didn't have already from the analysis of the integrated fluxes, but the central model does. If you increase the compacticity of your object, you can still see a shadow, even though there is no event horizon. But only if the compacticity is really high. If the compacticity is low, then you don't see a shadow. So let's take these two models, the ones that we had here, so the SBS2 and the SBS3, which are the nearly ultra compact and the ultra compact, let's take these two models and see what happens if we increase the inclination of your observation. And one more interesting thing happens here, which is the fact that, let's take SBS2, you know that there you see at low inclination that there is a dimming of radiation in the center. This is for 0 degrees of inclination. But if you increase your inclination to 20, 50, and 80 degrees, then you start seeing something interesting, which is the contrast between this ring of light in your image. The contrast between that ring of light and the shadow becomes dimmer and dimmer. And at some point, as you can see here, there is no shadow. There is a smaller intensity, that's for sure, but there is no contrast with the exterior. There's no dimming of radiation in the center. The image becomes smoother and you don't see this, this dimming in the center. But if your object is ultra compact, so if your object is compact enough to have a light ring, it doesn't matter what is the inclination at which you are observing, 0 degrees, 20 degrees, 50 degrees, or even 80 degrees, you always observe a shadow in the center because of this really strong gravitational redshift effect. And we can compare this between different models. So for example, this is what you observe for a black hole, this is what you observe for a fluid star, and this is what you observe for a boson star. The three of them are chosen in such a way that they are ultra compact. Well, black hole is always ultra compact, but the fluid star in here, chosen here, is also ultra compact. And you can see, well, the shadows are slightly smaller than for the black hole case, but all three models have a shadow, even though only the black hole has an event horizon. So the fluid star and the boson star, they also do not have event horizons. They both don't have event horizons, but they still present a shadow as long as they are compact enough to be ultra compact. Finally, one last thing I would like to mention is the effects of your spacetime, of your background spacetime in spectroscopy, and more precisely in the broadening of the Aaron lines in your observation. For all of the projects or all of the topics that I've talked about in this presentation, this is perhaps the one that I am the least familiar with. This was my first project on line broadening effects. It was done in collaboration with Daniela Perez and Joaquin Pelé. They are the specialists, so perhaps I will not be able to answer all of the questions you may have about this part of the presentation, but I want to mention it anyway because even though they are the main contributors, this is an effect where we can also distinguish between the black holes and the other models. So I believe it's interesting to have it in this presentation. But anyway, remain aware that this unfortunately this is not my biggest specialty. For all of the topics that I've spoken about, this is the one I am least familiar with. But let me try to nevertheless introduce you the best I can. So the idea behind this project is to check what happens to your spectral lines when you are observing emission from an accretion disk and from the corona around the accretion disk. What happens if you are observing this in a black hole spacetime, and what happens if you change the spacetime from a black hole to something else? Is there any effect, any visible effect, any difference between the spacetimes in what comes to your spectral lines? So as I mentioned before, if you want to do this with an accretion disk, it is necessary that your accretion disk is truncated at what is called the innermost stable circular orbit. So it is necessary that you have a region where orbits become unstable, and so the accretion disk does not stay there when you are making the simulation. And this is necessary because of what? Because before I just mentioned how we know this, or we anticipate this because the orbits become unstable. But is there a physical reason, a more connected to observations reason to mention that this must be like that? And the answer is yes. Because if you calculate the intensity profiles, the temperature profiles of your accretion disk, having and not having an innermost stable circular orbit, you find differences that are very difficult to explain. So in here I present you 7 models. The black line is the black hole, which is what you see here. SPS 1, 2, and 3, those are the solid tonic boson stars I presented before, so a very dilute one, one close to ultra compact and one that is ultra compact. And you can see that all these 3 lines stay very close to the black hole line. And then we have 3 additional models, this lambda BS1, lambda BS2, and lambda BS3. This is a different model of boson star. It doesn't really matter. What matters is that these 3 models do not have an innermost stable circular orbit. So the orbits, the circular orbits around these lambda boson stars, these orbits are stable all the way down to the center, unlike it happens for the black hole and like it happens for solid tonic boson stars. So what happens if you try to calculate the intensity or the temperature profiles in these models without an innermost stable circular orbit is that the temperatures are much bigger than what you observe. So this is the black hole case, the black line. All the others, all these 3 stay very close to the black hole case because there is an innermost stable circular orbit. So if there is an innermost stable circular orbit, an ISCO, if there is an ISCO, then below the value of the ISCO, you have a very, very low emission, very, very low temperature because orbits are unstable. But if you don't have that ISCO, you can have peaks of temperature very large, orders of magnitude larger than the black hole case, and very close to the center, which again is something that you don't observe. So this is what you see in our simulation. So in this case, we consider an accretion disk with these intensity profiles. I have the lambda BS3 here just for comparison. The lambda BS3 is this purple line that you see here. And if you just look at the image itself, it doesn't look very different, right? If you look at the lambda BS3 here, or if you compare it with the SBS3 and the black hole here, they are different, but just slightly different. It doesn't look too different. But now, look at the values of the intensity. If you look at the intensity here, the legend for the intensity, these peaks here correspond to an intensity equals to the maximum intensity, and in here the value of the white part here corresponds to a much 3 orders of magnitude lower value, as you can see from here, and these 2 are very close to each other. So if you don't have, and this is the first conclusion that we need to take, if you don't have an innermost stable circular orbit, so if your compact object is not compact enough to develop an ISCO, this means that the intensity profiles, the temperature profiles of accretion disks, hypothetical accretion disks around these models are incompatible with what you observe. And it doesn't happen anymore if your object has an ISCO, and especially if the ISCO is close to the black hole one. As you can see between these 2, you still see the additional images we have already discussed before, but the intensity profiles and the intensity of the accretion disk is very similar in both cases, which means that this model is comparable, is mimicking the black hole case, whereas this one is not by orders of magnitude. One final effect that I would like to call your attention to is the effect of this broadening of spectral lines. And to study this this effect, we have used the model for the corona called the lamppost corona model. This model is just an approximation. We know that if we have a corona, we have emission from different points in the corona. In this case, the lamppost corona model makes the approximation or the assumption that we have a single point emitting radiation in the corona of this model. And it's called lamppost corona because they assume, or the model assumes, that emission is being emitted, light is being emitted by a point on the vertical axis perpendicular to the equatorial plane. So what do you see if you look at this emission from the corona? Well, you will have, first of all, the primary emission, that is the emission that goes directly from the lamppost corona to the observer, and this corresponds to um, this corresponds to an intensity profile. So this is intensity as a function of radius on the observer screen. You observe the primary image as a single peak in your screen, and then you have a secondary or reflected portion corresponding to the photons that are emitted not in the direction of the observer, but they are first emitted in the direction of the accretion disk. They are reflected by the accretion disk, and it's the reflected photons that you observe in the observer screen. And the reflected profile looks something like this. If you combine these two effects, then the superposition of the two effects is what you observe in your detector. And these are the results of our simulation for different inclinations and for different values of the point of the position of the lamppost. So this value h that you see here on the left side, this corresponds to the position of the lamppost on top, or the distance between the lamppost and the central object. And what do we see here? Again, we have the results for the three boson star with different levels of compacticity. And what we see, once again, basically this is always the a result that we have, is that the more compact your boson star is, or the more compact your compact object is, the closer is your observation to the black hole case. So the black hole, for example, let's take this one on the top left corner. The black hole line corresponds to the black line. The SPS1 and SPS2 are the red and green lines respectively. And then the SPS3, which is the ultra compact one, is the one that is closest from all of the three SPSs. It's the one that is closest to the black hole case. And the same is true for most of the models. The SPS3, the ultra compact one, is the one that is always or mostly the closest to the black hole case. Exception being at very high inclination, as you can see in here, and in here. For very high inclination, it seems that SBS2 is closer to the black hole model than SBS3. But again, this means that very dilute models cannot be responsible to produce the observations that are comparable to the black hole case. So to finish everything, I will just leave you with my most important conclusions from this presentation. The first one is that we have shown that different types of observations from astrometry, polarimetry, shadows, and spectroscopy, these four types of observations can be used to test the black hole hypothesis, or to verify if a given model, if a given compact object is a black hole or not. Second point is that if you don't have an event horizon, then you have additional imprints on all of these observables, and they can be used to distinguish between the black hole case and the other cases. Third point is that independently of the type of compact object that you have, it doesn't matter if it's a gravitar star, it doesn't matter if it's a fluid star, it doesn't matter if it's a boson star. What matters is how compact your object is. If you have two objects fundamentally different from your matter type point of view, as long as they have similar levels of compacticity, they will have similar observational properties. And this is precisely the main point. Point number 4 is that only if your object is non-ultra compact, so only if your object does not have a light ring or a critical curve, only in this case, inclination plays an important role. As we have seen, if you don't have, for example, in the integrated fluxes, if you don't have a light ring, then the number of images you see depends on inclination. If you have a light ring, you will always see the same number of images. And the same thing is valid also for the shadows, for example. As I mentioned before, if you don't have for the shadows with inclination, for example, if you don't have a light ring, so if your model is non-ultra compact, when we inclined our observation, we saw that the shadow basically disappears. It smoothens out. So inclination makes a difference. But if you have a light ring, the shadow is always there, independently of inclination. So once again, inclination is only particularly important, is only a dominant effect or a large effect if you don't have a light ring. If you do, it becomes less important. 5 is that, as I mentioned also recently with this last slide, the previous to the one where I'm at now, ultra compact objects usually reproduce the observations better than the non-ultra compact ones. And the very dilute ones specifically, they immediately contradict both in the intensity profiles, in the emissions and the shadows, and in the astrometry. So you really need your object to be very compact in order to be able to reproduce the observations that you have. Point number 6 is that polarization immediately excludes models with low compacticity because you need a secondary image to reproduce the QU loops with two different sizes. If you don't have a secondary image, that is what happens when your model is a low compacticity model. You don't see this effect. So these models are immediately excluded by the observations of polarization. And finally, one result that I think from all of the results I presented in this talk, the one that I think is the most interesting is that you can still have shadows even in the absence of an event horizon, as long as your model is compact enough for the effects of gravitational redshift to produce a shadow. So all of these models, horizonless models, are still consistent. If they are ultra compact, they can still be consistent with the observations you have from the Event Horizon Telescope. So that's all from my side. Thank you very much. And if you have any questions, let me know.
Thank you, João, for this really nice talk. Are there any questions? Jutta?
Yeah, thank you very much from my side also. Very nice talk. I enjoyed it. I'm wondering about your model. I think you call it a central model, something like that. How do you model this precisely?
Yeah, so all of the analysis that we have done so far with the central model is a purely qualitative analysis. And we chose this model for the accretion disk because this paper by Gralha, Lupsaske, and Marone, they have shown that this distribution of intensities match very closely what you get from magnetohydrodynamic simulations. So this is one of the best ways to simulate the intensity of the accretion disk, but we don't have a quantitative result or a quantitative observation to base ourselves to make the central model. So when I say that we assume that there is emission from the center with a certain intensity from the center, this is all purely qualitative. We just chose our model in such a way as to present a peak of intensity at the center, but there is no observation, there is no simulation, at least that I know about, that allows you to make a precise choice on the values of the parameters such that this becomes realistic. We don't have that. So this is purely qualitative, and I don't have an answer for you about how to make this more realistic in terms of numbers.
Yeah, thank you. Yeah, I was wondering, you might be doing something. You did a lot of stuff with boson stars, so you have some matter accreting at the center of the boson star, so you get some fermion boson stars, some accumulation, this might finally give such modeling. But I don't know. It was just what came to my mind when
No,
I
agree completely. Yes, there's probably simulations that you can do to have a more precise idea of what the amount of intensity coming from the center is and what exactly is the profile of that intensity. I haven't done that. And I don't know any paper that has. But if that paper eventually comes up and someone models the intensity coming from the center, it would be in principle possible to refine the parameters of this model for the accretion disk in such a way that it represents more closely that. But so far, that has not been done.
Yeah, thank you. It's very interesting. Thank you.
Thank you.
Any other questions?
May I ask some questions?
Yes.
Sure.
Yeah, I actually have a few questions. Just maybe ask. So for example, in particular, in this central accretion emission model, I understand that if you have light rays that are emitted from the central parts, and because of the strong ratio, basically we cannot really see them. That's why the shadow image is dark in the center. But did you consider? I mean, there could still be some photons that originally they were outside and then they enter the surface and pass through the interior, pick up some intensity. I mean, they already picked up some intensity before entering the surface. And then after that, they escape again, and then we can observe them. Did you consider this light rays as well in the image? Because I suppose those light rays would not be would still be bright.
Yeah, so just to make sure that I understood, what you mean is that some photon that is emitted from the outside
Yeah,
goes in the center, superimposes with a photon coming from the center, and then
yeah,
what you observe in the observer is the sum of the two intensities. That's
yes.
perfectly possible, yes, and we haven't published that because as I mentioned, these two effects, so emission from the center and emission from the outside, they can be studied separately, which is what we have done here. So this is assuming only emissions from the center. This is assuming only emission from the accretion disk, but the reality would be the superposition of the two, as you're saying. If you make an inclined observation like this, and you consider the superposition of the two, you will see brightness coming from here, from the center. But this brightness is basically indistinguishable from the accretion disk itself. So it doesn't give you an additional imprint that is distinguishable from the accretion disk, because the intensity coming from the center, even if you have this superposition of photons coming from the accretion disk and photons being emitted from the center, if your model is compact enough, which is what happens, for example, here in the SBS tree, the intensity of the emission from the center is so low that even if you sum that intensity with the intensity for the accretion disk, it is just approximately equal to the accretion disk. So you don't have an additional effect on that. It looks basically the same.
But you can
But
still
of
see some
course, this
inner rings, right? Those brightness would just be inside the support that the region that is supposed to be dark.
can you repeat, please? Sorry.
I mean, you of course the intensity would be more or less the same as the usual accretion disk, because those light rays are those emission are collected before those photons enter the surface. But the impact parameters, I mean, they appear on the image as inner rings, which I mean are inside the region that is supposed to be dark for black holes, right? So I think you can still distinguish those emission
You
from.
But yes, but these are the ones that you see here. I think the additional images that you mention are the ones that you see here. And this is important. This is important. So you are totally right. This is what you see if you only have the primary, that is for the very low compacticity boson star. If you have a black hole, you will see this image and this image. And then if you don't have an event horizon, you see this additional one in the center.
Okay,
And the same thing
I
here.
see.
So if you have the black hole, you will see this image and this image. And then if you remove the event horizon, you will see also this one and this one. So there are indeed additional light rings in the center. And that's precisely what causes the shadow in the black hole to be slightly bigger than the shadows in these alternative objects, because the radiation that you see in this region here corresponds to the radiation coming from these inner light rings that you don't have. So you are totally right. There is additional light rings coming from there, but that doesn't remove the shadow. That just makes the shadow smaller.
Oh, I see.
And
Okay,
that's the reason why this shadow is bigger than these two.
I see. Thanks.
Are there other questions? If not, maybe I can ask one. From what I see, basically you look at spherically symmetric stars, right?
Yes.
Did you also try to look for those effects in rotating stars? I mean, for the Schwarzschild spacetime, then you get the asymmetry, which I guess would also appear to some degree here. But there's also this effect that the higher order images from co-rotating light rays kind of pull outwards, and then some of them may even become a bit better visible, although they would be
This
still, of course,
is
very
uh,
faint.
this is work that has not been done. No, this student that I mentioned, Daniela Cordeiro,
Mhm.
she is now starting her PhD, and the project that we proposed for her PhD includes generalizing all of the results that we or all of the observables that we have done here for boson stars. She will be generalizing that for rotating boson stars and for black holes with scalar hair. So that's the idea for her PhD. It's not been done, but hopefully she will be successful, and perhaps in a couple of years we will have some results on that. But so far it has not been done.
Oh, nice. Are there other questions?
Maybe I can ask one more.
Yeah.
Yeah, sure.
So in the QU loops, you mentioned that there's a significant difference between the models in the high inclination. I'm just wondering how high the inclination should be in this case.
Yeah, so in here this is for 80 degrees, and there is a transition from this to this. This is 20 degrees, this is 50, this is 80 degrees. I haven't done the simulation for 50. Usually I do 20,
Uh,
50, 80. I haven't done for 50, so I don't know exactly when the difference becomes dominant. But I would suspect that it should be. I think at around 50 degrees, this should already be strong enough for you to see differences like this. Because
I see.
what makes the biggest difference in this case and in this case, I can mention this because I think I didn't, is the fact that if you look at the Q values here, at low inclination you have negative values for Q and positive values for Q in all models, but at high inclination, only the SBS3 model has positive values for Q. All the others are negative. And that's a big difference. So I suspect that it should be around 50 degrees, or 50 degrees should be enough for you to already see models, or for you to already have these models, these three models, all in the negative region of Q. And that's what makes the biggest difference in the observation. So you don't need
Uh,
80 degrees for sure, because these for 80 degrees, these models are already very far from zero. But I would say you need at least 50 or 40, 50 degrees for this effect to appear.
so I see. Okay, so what if you go to the other side of the equatorial plane? Let's say, so this is 80. What if you go to like 110? No, 100. No, 100.
It doesn't make a difference, because this is symmetric independently of being above or below the equatorial plane. You just make you just make a reflection of this plot around the horizontal axis, I think. So it doesn't
Okay,
make
okay, okay.
a difference.
I see.
Yeah.
Thank you.
Thank you.
Okay, are there other questions? If not, maybe we end the official part of the seminar here. Thank you very much again for the nice talk.